Hello, and welcome back to Shiksha DaCosta. Today we're going to look at rational exponents as part of our unit on the graphs and equations of exponential functions. Today we're going to learn what does it mean when an exponent is a rational number that looks like this, and you're going to determine that through an investigation. To start us off by getting our minds in the right groove, let's find the side lengths of a square that has an area of 64. Basically, what that means is if I take this side and I multiply it by this side, length times width, they are actually both the same number, which we call s for side length. S times s would be s squared, and that should give us 64. To find out what s could be, I need to get rid of the square. If I want to isolate s, and I can take the square root, that would cancel it out. The square root of 64 is 8. So each of these sides could be 8. 8 by 8 would give me an area of 64. What if it was a cube that has a volume of 64? Well, the volume is all the space that's on the inside, and the way we calculate volume is length times width times height. But if they're all the same, they're all s, this would be s times s times s is s cubed. And if I take the cubed root now of s, and in other words, this is asking what number times itself 3 times gives us this. Well, the cube root and the exponent of 3, the cubic power, cancel each other out. And because I did it to one side, I have to do it to the other side. What number times itself 3 times gives us 64? You can pause the video if you'd like to think about that for a minute. The answer is actually 4. So all these 3 sides have a length of 4. Let's connect that now to rational exponents. So here we have a square. It's got a side length of x and x. What's the area? Well, length times width would obviously tell us the area is x squared. But what I'm going to do now is I'm going to try and go backwards. What if I said, okay, the area of this square is a. Can you express the as x? Can you express x as a power that has a as the base? In other words, can you say that x is equal to some power where the base of the power is the area of this square? I'm going to walk you through this because it's actually kind of a weird way to think about this experiment. And I'm not sure really there's anyone on this planet that would be able to figure this out without some guidance. So here I have x, and I know that x times itself would be x squared. So if I actually replace x in this equation, wherever I see an x, if I replace it with a to the power of n, I'd get something that looks like this. Look, I've changed x into a to the power of n, x into a to the power of n, and x into a to the power of n. And I've squared all of that because that was what this equation looked like. Now, why did I change it? What allowed me to change it is just this. I'm saying x is equal to some power of a. Now, in this case, I'm taking the a from this side. This a must be equal to a to the power of 2n. And I got 2n just by multiplying these two using the power law of exponents. Now, if this equation is true, and I think it is true just based off the fact that I found the area of the square, and I'm just trying to express x as a power of a, the only way for this to be true is if the exponents are the same as well, because the bases are the same in this case. The exponent on this is just 1. So 1 must equal to 2 times some number n, and that's what I'm looking for. Can I express x as a to the power of some number? What does that number have to be? Well, I can find that out because if the two bases are equal and the exponents are equal, now I can just isolate n by dividing both sides by 2 here. And I find out that n needs to be 1/2. What does this mean? How does this help us understand rational exponents? Well, this means that the side length of a square that has an area of a, the side length can be expressed by a to the power of 1/2. Now, I know you must be thinking, hang on, if I want to find the side length of a square with area a, I would just square root it, right? Don't we just square root that? Well, yes. And actually, today, one of the things we're discovering or learning is that this is another way to say take the square root. This is the big learning, or at least some of it. Anything to the power of 1/2 is the same thing as taking the square root of that number. Let's Does this idea extend to bigger powers? Well, if this is a volume of a cube, the volume of the cube is x times x would be x cubed. And if I wanted to find the side length of a cube that has volume v, very similarly, if I'm trying to express x as a power of v, I could say something like this. X must be equal to v to the power of some number. What is that number? Well, if I look at this equation and I replace everywhere I see an x with what I know x is actually equal to, which is v to the power of n, then my equation will start to look like this. And v to the power of n times itself 3 times is v to the power of n cubed, obviously. And so the volume of the cube must equal, this power of v to the power of n times itself 3 times. And I can use the power law to simplify that to 3n. Now, the only way for this to be true, because the bases are the same, the only way that this is the left side equals the right side is if the exponents are the same as well. This v has an exponent of 1, and therefore 1 must be equal to 3n somehow, right? And this will help me find the value of n. All I have to do is divide both sides by 3 to find out that n is equal to 1/3. But again, I moved pretty quickly through this. What does all of this mean? Well, it means that if I have a cube with volume v, then each side length would have a length of v to the power of 1/3. And again, you must be thinking to yourself, well, hold on. If I wanted to find the side length, I could just take the cube root of v. And in fact, that means the same thing as well. V to the power of 1/3 means the exact same thing as the cube root of v. So in this little investigation, we came up with these two things. And I don't know if you've noticed, but there's a little bit of a pattern here, right? And this is actually true for all roots. Anything to the power of 1/n is equal to the nth root of that number, of that base. Whenever we have a rational exponent, we can always turn it into a radical or a root, only if the numerator is 1, though. But what if it isn't? Today we also will learn what to do if it isn't, and there's kind of a really an elegant solution to figuring this out, and I'm going to walk you through it right now. For example, what if you have 8 to the power of 2/3? Well, this is not 1/3. I can't just take the cube root. Well, what I'm going to do is I'm going to look at the fraction here, and I'm going to do something that's a little strange. It might look complicated at first. You'll see why I'm doing it in a second. I could take the number 2/3, and I could rewrite it as 1 times 2 over 3 times 1. Multiplying it by 1 doesn't actually change the value of the top or the bottom. Now, when we're multiplying fractions, usually we can just multiply the numerators and multiply the denominators, just like this, right? A over B times C over D, A times C, B times D. But now, instead of going forwards, I actually already have a situation that looks like this. So I'm going to go backwards and split this up into 1/3 times 2/1. And further, 2 divided by 1 is just 2. So I've said, okay, 2/3 is the same thing as 1/3 times 2. And if I had this exponent to the power of 2/3, I can split it up into 1/3 times 2. But I'm not done yet. I can even work a little bit further with this, right? And really the question here is, why did I even bother doing this? Doesn't this look like more work than this? There's a multiplication operation, whereas over here I just had division. Well, to really see the genius, you actually have to do one more going backwards step. And we're going to undo the power law here. The power law of exponents says that if you have a power of a power, you could just take those two exponents and multiply them together, right? Well, I have something that looks like this right now. And instead of having a power of a power and turning that and multiplying the two exponents, I already have two exponents being multiplied. So I'm going to go back and turn this into 8 to the power of 1/3, and then all of that to the power of 2. This is now a power of a power. How did this actually help us? Well, 8 to the power of 1/3, I know what to do with that, right? That could just be the cube root of 8. And then I can take all of that and I can square it. The cube root of 8, what number times itself 3 times gives us 8? That's 2. And 2 times itself twice is 4. So I was able to evaluate this, this power that has a rational exponent without ever needing a calculator. And in fact, this is true for any power that has a rational exponent, b to the power of m over n. We can take m over n and split it up, just like we did over here. We can split that into two separate fractions. And then for this one, we'll keep it the way it is. M divided by 1 is just m. And then we can go backwards using the opposite of the power law. This is 1 over n all to the power of m. And this right here is the same thing as this. And so we can change it to the nth root of b and make that all to the power of m. So when you're simplifying algebraic expressions, the custom is always to give the final answer with positive exponents. If you have a negative exponent, you can move it to the denominator to make it positive and vice versa. But a number that is raised to a rational exponent is actually equivalent to what's called a radical or a root. The radical exponent 1 over n is the nth root of the base. But if the numerator is not 1, like an exponent that looks like this, m over n, then you can instead change it to this or this. And either one I think works, but I think this one is my preference. You could just take the nth root of a and then take all of that to the power of m. In this example, I'll kind of show you how that works. So we have x to the power of negative 3 over 2 over x to the power of 2, but I'll just use my regular exponent laws like the quotient rule, which is I'm dividing two powers that have the same base. So I can just subtract them. So negative 3 over 2 minus 2. Let's make them have the same denominator of 2. So negative 3 minus 4 is actually negative 7. Now let's use the rule that we already know about negative exponents. We can take the entire power and move it into the denominator and change that exponent to positive. From there, we can use the law for rational exponents to make this 7 over 1 times 1 over 2. And this would just be x to the power of 7, all to the power of 1 over 2. And of course, the power of 1 over 2 means take the square root. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.